As an example, let's calculate the partition function of the ideal gas in the microcanonical ensemble. We will use the classical description of the partition function. The gas that we are considering is the gas that surrounds us. It's made up of particles, molecules, which have a given mass, and the Hamiltonian of this gas is solely given by the kinetic energy of its particles. Hence, the Hamiltonian H of P or Q is only dependent on the momentum P of all those particles and is given by P squared divided by 2m. You have to realize that P in this case is actually a 3n vector. Thus, the total Hamiltonian reads H is equal to 1 divided by 2m, sum of on all particles 1 to n, pi squared. What we considered here is the dispersion relation of a non-relativistic particle of mass m. The dispersion relation describes how the energy of a particle changes with momentum pi. There are also other types of dispersion relations we know of. One would be, for example, a relativistic or massless particle like the photon, where the energy scales linearly with the momentum of the particle. Now the Hamiltonian that we just found, we need to insert into the partition equation where it appears in the delta function. Now let's rewrite the delta function that we obtained, and we get that the delta function is equal to a delta function of p squared minus 2me. In order to understand what this is, it's helpful to consider a particle, just one particle, in a 2D space. In this case, the delta function only gives a value if px squared plus py squared is equal to 2me. This is describing a circle in this two-dimensional phase space of that one particle. Now it's easy to further extend this view, hence the delta function of p squared minus 2me solely describes a surface of a 3n dimensional sphere. The surface and volume of an n sphere you can read up, for example, in Wikipedia. What you will find is that the surface of the n sphere is given by 2 pi to the power n half divided by gamma of n half times the radius of the sphere to the power n minus 1, one dimensional lower than the volume of the sphere. Now we can return to the partition function of the ideal gas. As the first step, we integrate on the spatial coordinate dq3n. This will yield the volume to the power n. Then we turn to the integration of the momentum variable p. We just saw that the 3n dimensional delta function in this case describes a surface on a 3n dimensional sphere. Thus the 3n dimensional integral turns into a one-dimensional integral on p from 0 to infinity, p to the power 3n minus 1 delta of 2me minus p squared. Now change in variables and knowing that integration on the delta function just picks the value at which the delta function is equal to 0, we obtain the final solution, which is that that omega of n, e, and v is given by v to the power n divided by n factorial h to the power 3n pi to the power 3n half divided by gamma of 3n half times 2me to the power 3n half times delta E divided by E. The latter factor we obtain as of the volume of a surface equals to 0. So what we calculate here is the partition function for a system which energy is between E and E plus delta E. The expression can be further simplified using Stirling's approximation that n factorial is equal to n to the power n for very large n, or the gamma function of x is equal to x to the power x. The partition function omega of the ideal gas in the microcanonical ensemble gets very easy. Reading omega of n, e, and v is about v divided by n divided by lambda thermal to the power 3 to the power n times delta E divided by E, where lambda thermal is the thermal de Broglie wavelength given by the square root of 3h squared divided by 4 pi m n divided by E. The thermal de Broglie wavelength is the equivalent of the de Broglie wavelength that you might know from quantum mechanics in statistical physics. The thermal de Broglie wavelength scales with 1 divided by the energy of the particle. Oxygen molecules that fly at a speed of 300 meters per second, the speed of sound, have a de Broglie wavelength, which is well below the size of an atom. If an oxygen molecule is flying at 100 kilometers per hour, its de Broglie wavelength is on the order of less than a nanometer. Only those molecules that fly at an extremely slow pace of 1 centimeter per second have a sizable de Broglie wavelength on the order of a micron. So in summary, what we derived is the partition function of the ideal gas in the microcanonical ensemble omega of n, e, and v. What we found is that the partition function is given by the mean volume per particle divided by the thermal de Broglie wavelength to the power 3 to the power n times delta E divided by E. Omega thus tells us what is the ratio between the available volume for a single particle as compared to its size in terms of statistical mechanics as given by the thermal de Broglie wavelength cubed.